Okay, so we're going to start a new chapter of mechanics, and this is going to involve the idea of moving objects, exploring how fast they're going, how long it takes for them to cover certain distances, and all of this is kind of under this umbrella of constant acceleration. So the idea that things that are moving will sometimes be increasing or decreasing in speed, and that this increasing or decreasing rate is constant. So that's sort of our general topic, is constant acceleration. But we'll talk about that a little bit more next time. For this first sort of session, we're just going to look at displacement time graphs and velocity time graphs, make sure we understand what information we can get from them and get an intuition for what they look like in terms of how they can describe certain situations. Before we then start with that though, I've got a question here for you. I'm going to say now, it might not be as obvious as you think. The obvious answer is not going to be the answer. So if you're at the end of a road, 1 kilometer long, or if I'm at the end of such a road, and I run to the end of that 1 kilometers, I do it at 6 meters per second, and then I turn around and immediately run back at a constant rate of 4 meters per second, then on average, throughout that entire situation, what was my average velocity? Before I tell you the answer, see if you can just get a number in your head of what you think it might be. Okay, and to just give you one last chance to double check what you're thinking, be aware that I asked for average velocity as opposed to average speed, and see if that influences your answer. And then I will reveal that in fact the average speed for this specific scenario is in fact 0. Okay, and why that is, we're actually going to look at on the next slide. Okay, and we'll just clarify why in this case is it 0, as opposed to perhaps some of you thought it might be 5, but that will be the average speed is 5. Why is the average velocity 0? Let's take a look. Okay, so we have here the title of average speed and average velocity, and what is the difference between them? There is a difference, and it's a bit subtle. And ultimately, the difference comes from the difference between distance and displacement. So let's just remind ourselves what those were. Distance is always positive, and displacement can be positive or negative. In one dimension. So effectively, displacement takes into account direction, and distance does not take into account direction. So for instance, if I consider that situation from before, if I ran 1 kilometer and ran back 1 kilometer, the total distance is 2 kilometers, but the total displacement is 0 kilometers, because displacement is measuring my final position taking away my initial position. In this case, if I start where I end, my displacement is 0, regardless of how far I may have traveled in between. So then let's define average speed, average velocity, and they're probably what you expect them to be, but then just be aware of the difference. So the average speed is your total distance divided by your time taken, right? And your average velocity, however, is your, I guess we don't even need to use the word total, we can just say displacement. Okay, your displacement over time taken. So in the example we had, the total distance was 2 kilometers, and the time taken was some amount of time. And if you work it out, then yes, you could probably decide on an average speed. But the average velocity, regardless of the time taken, if the displacement is 0, then the average velocity is 0, which was the case for that previous one. So in fact, the fact that the length of the road was given was irrelevant. The 6 and the 4, all of that was irrelevant. Every number in that question was irrelevant. The only thing that mattered was that the end was the same as the start, and therefore displacement is 0, so your average velocity is 0. So just a bit of a trick question to make you aware of this key difference. So having clearly defined those two types of average, let's take a look at our first set of graphs, displacement time graphs. So here we have 3 graphs, and on the x-axis we've got time, t, and on the y-axis we've got displacement, which is commonly measured with the letter s rather than the letter d. And that will be consistent throughout the sort of mechanics topic. We'll tend to use s to refer to displacement. In the brackets you've got the units, so we've got seconds versus meters, though for our purposes that doesn't matter in terms of what the graph looks like. The question ultimately then is, what kind of motion is being described in each of these 3 situations? So you've got displacement being plotted against time for a specific object. So there's some object which did some movement, and you've got this graph, and then let's say object B moved in such a way it looked like this, and this one's object C. Have a think, and then I'll give you the answers. What kind of motion is being described in each of these cases? Is the object moving? How fast is it moving? Is the speed changing? Those are your sort of key questions. So have a think for a moment, pause the video. Okay, let's take a look. So it's a bit wordy, but let's just sum up. So in the first case, there's no change in the displacement over time. Object is stationary. So that's the key word, that's stationary. Which makes sense, right? Because no matter what time you're checking, whether it's at the start or it's at the end, this displacement value, whatever it is the same throughout. So this is a stationary object, is an object that's not moving at all. In the second case, we've got the displacement increases at a constant rate over time, and the object is moving with constant velocity. So this is a constant velocity. So we're looking at an object which is moving, and it's moving at a constant speed. 5 meters per second, 10 meters per second, doesn't matter what the number is, but it's a constant speed. And then we want to contrast that with the third graph. In this case, the displacement is increasing, so likewise here it's increasing, right? That's an increasing function, so is this one, so that's still the same for both, but the rate of increase is itself increasing, right? So the displacement is increasing at a greater rate as time increases. The velocity is increasing and the object is accelerating. So the object is accelerating ultimately. So to just clarify what features of these graphs correspond to these underlined section, in the first case it's because it's a horizontal line. So in a displacement time graph, and let's be clear, we're talking displacement time, not velocity time. In a displacement time graph, a horizontal line is a stationary object. Let's say non-horizontal straight line is constant velocity, or at least a non-zero constant velocity. And let's say here a curved slash polynomial line means the object is accelerating, right? So a non-straight line means it could be accelerating or it could be decelerating. Those terms effectively mean the same thing. It's just you're talking about whether the speed is increasing or decreasing. Either way, it's not a straight line. Okay, so what you'll often see is in a displacement time graph, you'll have a mishmash of all these 3 different shapes. So you'll have, a line graph which might be straight, and then it might go at a diagonal, and then it might curve a little bit. And for each of those sections, you want to break it down so you can understand what's happening. Maybe it was stationary for a bit, then it had some constant velocity, and then it accelerated. Maybe it was stationary again. Okay, so make sure we can make the association and that you can justify in your head why it's the case. Okay, and then before we look at the other version, the velocity time graphs, our second type of graph, let's do one example with the displacement time graph. So you've got a cyclist riding in a straight line for 20 minutes. That corresponds to this part here. That's 20. Just to be clear, and let's be picky and just point out a few things. The fact that it's a straight line here has absolutely nothing to do with the fact that this is a straight line here, right? That straight line is referring to her direction of motion. So it's just saying this is a one-dimensional problem. It hasn't got anything to do with the fact that this section is a straight line. She waits for half an hour. Okay, so then the waiting for half an hour, that's this bit, isn't it? Right, she waits for 20 plus 30 minutes, it's 50. That's our wait. Let's put that there. So there's wait. So it's a ride, then a wait, and then she returns again in a straight line to her starting point. So again, they're just clarifying that it's back in exactly the same direction, but well, same direction but opposite, parallel, I suppose. Back to her starting point in 15 minutes, right? So then this this final part, 15 minutes, so it goes all the way up to 65. That's a ride back. Okay, work out the average velocity for each stage of the journey. So before we do that, just to clarify again, from looking at the graph, you should be able to immediately tell yourself, right, she started at time 0, she was at the beginning of her journey. Then she was cycling at constant speed, not accelerating. Then she stopped, rested for 30 minutes, and then cycled back, and again at a constant speed. And this time, the reason it goes down rather than up is because she's changed direction. If she cycled for 20 minutes, rested, and then 15 minutes again, but in the same straight line without turning back, then this line would be going upwards still, right? Because her displacement would be increasing. But we know because she ends where she starts, it has to go back to 0, back to a displacement of 0. Right, so let's look at the actual questions. Work out the average velocity for each stage of the journey in kilometers per hour. Okay, so first off, let's just break it up into the 3 stages. So let's call it stage A, stage B, and stage C. And then let's work out the average velocity for each. So I won't write the formula, but I'll just state it again. Average velocity is displacement over time taken. So for stage A, what's the displacement? She goes from 0 to 5, positive 5, so that's a 5 displacement. And the amount of time taken was 20 minutes. Right, and we want kilometers per hour, so I think we're going to have to change that in a little bit. Or perhaps we could do that now. So rather than writing 20 here, right, we need to be cautious, don't we? Because this is kilometers per hour, whereas our graph says kilometers against minutes. So 20 minutes, that's a third of an hour. So let's actually just say divide by a third. Okay, so 5 divided by a third, we get 15 kilometers per hour. Okay, and then part B, what's the displacement? That one's easy. 0 displacement, right? She starts at 5, at a distance of 5, and remains at a distance of 5 by the end of the 30 minutes. So this is technically 0 divided by half an hour, 1/2, but the length of time doesn't matter, it's still 0 ultimately, kilometers an hour. And then finally, we've got starting at a distance 5, ending at displacement 0. So that's a displacement of -5, right? So average velocity can be negative because displacement can be negative. And that's over how long? 15 minutes, that's a quarter of an hour, 1/4. So we get -20 kilometers an hour. Okay, and then for part B, write down the average velocity for the whole journey Now here's what you don't do. What you don't do is then find the average of all three, right? That's not going to give me the correct answer at all, because the average of if you average a collection of averages, that doesn't necessarily give me the average of the whole thing, right? And we can see why, in particular, because here, what is the total displacement of the whole journey is 0. So this is just like my sort of trick question at the very beginning. The average velocity is just 0, right? For part B, it's just 0 kilometers per hour, because the total displacement of this cyclist is 0. Right, 0 divided by 65 minutes. And then work out the average speed for the whole journey. Right, okay. So the average speed, let's call this part C, remember, is going to be total distance divided by time taken. So now it's not as easy, although still not too bad. What's the total distance? So you just have to work through her journey. She started at 0, ended at 5, so that's 5 already, then sat still for a bit, and then travelled 5 again all the way back to the start. So her total distance is 10 kilometers. How long did she spend doing all this? It was 65 minutes. Again, well, it's asked for kilometers per hour in the previous question, so let's stick with that. 65 minutes in terms of hours is just going to be 65 over 60. So a bit of an unwieldy fraction, but 10 divided by 65 over 60 is then 600 over 65, which gives me approximately 9.23 kilometers an hour. Okay, and that's it. Got the average speed. Okay, so now let's look at velocity time graphs. So same thing again, like displacement time, but now your answers are going to be different, because now we're not plotting displacement against time, we're plotting the velocity of an object against time. For that first graph, there is actually a line there. It's just a bit hard to see. It's a horizontal flat line along the x-axis. Okay, so have a think, pause. What do you think is going on? Is the object moving? Is it constant speed? Is it accelerating? Okay, so the answers are the same as the previous set of 3, right? But the graphs, of course, are different. So same answers, different question, effectively. This one is stationary. This second one is constant velocity. And then this third one is constant acceleration. Okay, and again, you just need to make sure you've convinced yourself of why that's the case. It's not just a case of memorizing the shape. You want to understand why is that the case, and hopefully it should make sense. In the first instance here, that invisible horizontal line on the x-axis, it's at all times its velocity is 0, right? Because the 0 marker is the x-axis for that y-axis, which is v. So the velocity is 0 at all time, it must be stationary. In this case, our velocity is some value, a positive value, but again it stays the same. So here it's a constant velocity of 0, i.e. stationary, and here it's a constant positive velocity. So that's why we get constant velocity. And then here you've got a straight line again. On a velocity time graph, that means constant acceleration, because you've effectively got an initial speed which steadily increases, and the fact that it's steadily increasing along a straight line rather than a curve means it's constant acceleration. So then what's missing from this is, what if you had a velocity time graph which was curvy? Then you're looking at something where the acceleration is itself accelerating, and that gets a little bit more advanced. But as I said, the umbrella term for all of this topic that we're looking at this session and the next few is constant acceleration. So we're not going to have to worry about that having a curve on a velocity time graph. Effectively, a displacement time graph and a velocity time graph are a different way of viewing the same information. So you can go from one to the other. Largely speaking, there are a few unknowns potentially, but if you're given a velocity time graph, you can usually get a displacement time graph, and from a displacement you almost can get the original velocity time graph. Think of them as different views of the same scenario. Okay, so before we do two more examples and then give you questions, I want to just do a final summary so that we don't get confused, because I feel like it's very easy to confuse what a straight line means, for instance, on these graphs, if you forget which one's the displacement one, which one's the velocity one. So let's see it all together in one table. So we're going to do displacement time versus velocity time graph, and there's a few key things which we want to be able to compare, which are what is the meaning of the y value, what is the meaning of the gradient, and what is the meaning of the area under the curve. And that those two, gradient and area under the curve, we haven't explicitly talked about them yet. And finally, what constant speed looks like. I'll also put here. Because I think that's an easy one to get confused on. Okay, so on a displacement time graph, what is the y value of the graph? If I pick any point on the graph, what is the y value telling me? Should be obvious. It's a displacement time graph. The displacement is the y value, the time is the x value. Shows me displacement, right? On a velocity time graph, it shows me velocity. Okay. And then what about the gradient? So on a displacement time graph, think about what a gradient is. Right, a gradient ultimately is difference in y over difference in x, right? I'm going to put that in brackets here. Let's say difference in y over difference in x. Okay. So what is the y value? It's displacement. What is the x value? It's time. So it's displacement over time, right? So in this case, it's displacement over time. And what is that? It's velocity. Okay, so the gradient of a displacement time graph tells you the velocity of an object. Okay, and on a velocity time graph, the gradient will be the y, which is velocity, divided by the x, which is time, and velocity over time, that's the definition of acceleration. Okay, so if I have a velocity time graph and I want to know what the acceleration is that this object is experiencing, I can calculate the gradient of that line. Okay, and then finally, area under the curve. Let's just focus on the velocity time graph for a moment first. So area under the curve, I mean, how do you calculate area? It's height times width, right? So in some sense, it's kind of like multiplying x by y. A bit of a simplification, but it's going to help us remember what the meaning is. It's effectively x times y. So on a velocity time graph, it's effectively velocity times time. What is velocity times time? Well, velocity is displacement over time, so multiply it by time, and you just get back to displacement. So velocity time graphs are great because they can show all three things. A velocity time graph shows you the velocity, that's the y value, the acceleration, which is the gradient, and the displacement, which is the area under the curve. The displacement time graph, however, can only really show you displacement and velocity in an accurate way You can know that there's acceleration going on, remember, if it's curvy, but it's hard to know exactly what the value of that acceleration is. But what about area under the curve? Well, in this case, effectively, I think there is a value. I did look it up, but it's basically not used. I'm not even going to mention it. There's no real meaningful thing that we're going to put to this. I think some people have attempted to put some sort of meaning to it, which you can usually give meaning to things in mathematics and in mechanics, but it's not used very often, and you're not going to learn about it. It's not in the textbook, it's not in exams, so there's no point really mentioning it. So we're going to leave it blank, and you're not going to need to use it. It doesn't come up very often. It's neither acceleration, displacement, or velocity. It's something else which we don't need to worry about. Okay, and then finally, to just confirm, what does constant speed look like on a displacement time graph and on a velocity time graph? We just want to be completely clear on this. On a displacement time graph, constant speed looks like lines like this. Okay, so that's 3 examples in one there. And on a velocity time graph, it looks like this. Okay, and you've got a few examples there. Okay, so that's the difference that we just want to make clear. I think for consistency, actually, and to be more accurate, I'm going to call this what constant velocity looks like as well. Okay, cool. So that's sort of your summary of those. We're going to be looking at a couple of examples now, mainly velocity time. So we just want to make sure we've got these things clear in our heads. On a velocity time graph, the gradient of a velocity time graph is acceleration. The area underneath a velocity time graph is displacement. So with those two in mind, let's take a look at a couple of examples. Okay, we've got a velocity time graph illustrating the motion of a cyclist moving along a straight road for a period of 12 seconds. So that's the whole thing. For the first 8, she moves at a constant speed of 6, which is marked here. We can see it's a constant speed because it's a horizontal line. She then decelerates at a constant rate. So that's a form of constant acceleration. It's just constant deceleration, stopping after a further 4 seconds. Right, so there's our deceleration. That's deceleration. Notice, by the way, that what is the gradient of this? Is it positive or negative? It's negative, right? So because this is a negative gradient, it's negative acceleration. So that effectively is what we mean by deceleration, is a negative acceleration here. Right, let's answer the actual question then. Find the displacement from the starting point of the cyclist after this 12-second period. So what did we say displacement corresponds to on a velocity time graph? On a velocity time graph, it corresponds to the area. So now we think about what is the range of time I'm interested in, and in more complex questions it might vary, but in this case it just says the 12-second period. So we're going to start at 0 and go up to 12, and we're going to find this area. Okay, and if we find that area, that will give me the displacement. So we chop it up into 2 sections. Here we go. This area here is 8 times 6, nice and easy, 48. And then what about this one? Well, this is going to be effectively half. I don't know if this is square or not, by the way. In fact, we'll see in a moment it's not. This is a height of 6, and this is a width of 4, but it's a triangle. It's just half base times height, isn't it? So we're going to do a half times 4 times 6, and we get 12. So then add those two together, those two areas, and we get the number 60. So in this case, the answer is 60 meters. Okay, cyclist traveled 60 meters. That's the total displacement. Okay, and then work out the rate at which the cyclist decelerates. Okay, so decelerates, which is really just the same thing as acceleration, but negative. So we're gonna put a positive number to this, but it's effectively corresponding to a negative acceleration. That's just the gradient, right? So what's the gradient of that specific part? The gradient of that line here. So the gradient of the line is difference in y over difference in x. We can see that it's gone down -6, and it's on the x direction gone upwards by 4. It's increased by 4, so -6 over 4 is -3 over 2. However, technically the question asks what's the rate of deceleration, so we're just going to take away the minus sign, right? So the acceleration is -3 over 2, but the deceleration we'll say is just 3 over 2, which is in this case 1.5 meters per second squared. Okay, cool. So that example should demonstrate to you this idea of using the area and the gradient to pluck information from these velocity time graphs. Let's do one more example and then we're done. Okay, a particle moves along a straight line. Again, this thing about straight line, the reason they tell you this is just so that you know we're talking about a one-dimensional problem. So it's not happening in 2D. That'll be for later. So a particle moves in one dimension. It accelerates uniformly from rest. This accelerates uniformly is just another way of saying constant acceleration. From rest to a velocity of 8 meters per second in t seconds. So from rest, which is 0, to 8 in t seconds. The particle then travels at a constant velocity of 8 meters per second for 5 t seconds, so 5 times the length of time as what happened a moment ago. And the particle then decelerates uniformly to rest in a further 40 seconds. Sketch a velocity time graph. Okay, let's sketch the velocity time graph. So to answer questions like this, let's say you were just asked immediately find the value of t. You'd want to start with drawing the graph anyway. So the graph is in itself useful. It's not just asking you to draw one, to test your knowledge necessarily. It's a useful skill. So we've got time on the x-axis. We've got velocity. Let's mark it clearly on the y-axis. Let's see what happens. So let's do some key values. It starts at rest, so that means the graph will go through the origin, and then at some point it's at 8 meters per second after some amount of time. Don't know how long. I just know that it's capital T. Right, so after t time, it's at that point there, and I know this is a straight line because we were told that it accelerates uniformly. So it's not a curved line. And then it travels at a constant velocity for 5t seconds. So 5t later, it's still going at the same speed, right? It's still same speed because it's constant velocity, and that corresponds to a big horizontal line, constant speed for 5t. And then it decelerates uniformly to rest in a further 40 seconds. So it's going to go, we don't know, whether t is more than 40, less than 40. It doesn't really matter. We'll just mark it on. We'll find out later what the actual t value is. But we know it comes back to rest, so it comes back down to the x-axis. Again, a straight line because it said it decelerated uniformly. Okay, that's the best I can do for a straight line. Right, So we've sketched it and we've put on the key values, I think. Is there anything else missing? We've got 40, we've got 8, we've put 5t, we've put t. That's fine. Given that the total displacement of the particle is 600 meters, find the value of t. So now this is actually turning into a geometry question. Right, so we're using our understanding of mechanics to then create a geometry question. The total area under this graph is 600. Right, that's what they've just told us, because the total displacement is 600. So what do we do? Hopefully it's clear. We're going to basically create an equation from our understanding of the geometry of this situation. So let's calculate the area. We split it into 3 sections. Let's call them A, B, and C. A is clearly 8 times t divided by 2. Base times height divided by 2 for the triangle. B is 600, no, sorry, not 600, is 8 times 5t. Width times height. And C is 8 times 40, again divided by 2. So with a little bit of simplification, we should end up with this, and that's all equal to 600. So let's write our final equation. Add that all up. We've got 40t plus 160 equals 600. And then with a bit of rearranging, we should get t is equal to 600 minus 160 is 440 divided by 44, 10. 10 seconds. And that's our answer. Okay. Cool. So hopefully that all made sense. One of the key, bits of information from this is probably that table, which is telling you what all the aspects of a velocity time and a displacement time graph are. So make sure you've really taken a note of that one. We're going to be using it a lot, and you're going to be using it for the questions we're about to look at. So let's take a look at some questions and see how you do on them. Okay, so 4 questions total across 3 slides. They might look a little bit wordy, but I don't think they'll take you that long. Particularly this one here. This is more of just making sure you've understood these various concepts. What does the gradient correspond to? What does the y value correspond to? That sort of thing. So give this one a go. You can pause the video now. Okay, and then we're on to velocity time graphs. So take a look at this, think about gradients, think about area, and see if you can answer those 3 parts. You can pause the video now. Okay, and then finally, since this is a longer video, don't worry if you don't have time for both. Although, as always, if you have time for the practice, get the practice in. But please try at least one of these. Ideally both if you can. More problem solving style. See how you do. You can pause the video now.